going to be talking about applications. When do we use each of these things and why? And one of the simplest ways for me to explain the application idea is through speed and distance. That tends to be something very applicable that we can all understand. And what I really want you to focus on is the terminology a little bit here, as well as the units that I'm using. What I want versus what I have. I think that really makes a big difference in whether a student can understand an application and why we're doing what we're doing. So really watch these units in this video and why I'm choosing to do what I'm doing. Keep in mind the ideas that this derivative is all about slope, rise over run, change in y over change in x. That's the whole idea behind a derivative. Integral is area under. It comes from this idea of length times width. Lots of rectangles. We learned about that. Okay, essentially lots of rectangles underneath is kind of where the idea comes from. So if we keep those two kind of concepts in mind, I hope this will be as clear as possible. And of course, we're going to go over this again together in class. So let's start off with this idea of what I have in this first set. So in this first set, I have a function, a formula that's representing distance. So I'm able to obtain a formula that tells me the distance I have traveled over x minutes. So here I have my f at x, my function is representing kilometers, my x-axis is in minutes. So this line here will tell me how far I have traveled. So if I go to, say, right here, okay, at about 2 minutes, it looks like I have traveled a little less than 3 kilometers, maybe like 2.75 kilometers, according to this. So in terms of what I get, if I input x equals maybe 2 into here, I might get that I've gone about 2.75 kilometers. All right. But if someone says, hey, I want you to, I'm not really concerned about the distance you went. I'm curious about your speed. How fast were you going? Well, my graph doesn't show me anything about speed, and I need to understand what the relationship is between speed and what I have here. So I want you to think about what speed would mean when you're talking about kilometers and minutes. So when we think of speed, we should think of things like kilometers per hour, meters per second. We think of those, and we know that speed is a rate. Okay, it's a rate. And when I think of speed as a rate, I think kilometers per hour, meters per second. I'm thinking of this distance over time. My y over my x, my y over x. So what I essentially want is I want a new function that's not going to represent kilometers anymore. I want it to represent a new item, y over x, kilometers over minutes. And what do I know in terms of concept that's going to do y over x? Slope. Slope finds me the change in y over the change in x. Slope is about going from something like distance to a rate. Right? Slope will find me rate of change. It adds that unit of the x value. It essentially changes your function from y to y over x. It adds that extra, it finds that slope, that y over x, that meters per second. So when someone wants to talk about slope, because they're looking for a rate of change, we need a derivative. So if I go back up to here, my distance function, and I start taking the derivative, 3x squared minus 12x plus 9. This is the function for rate of change now, or speed, kilometers per minute. So when someone does the derivative, what they're asking for is, hey, I want a function that finds this over this. It's a rate of change. It's how something is changing as opposed to how it's starting off originally as kilometers, in this case, distance. So if I were to say, okay, well, it looks like the distance you're traveling at around X is 2, is maybe a little less than 3 kilometers. This is not perfectly to scale, so these might not match. But that would be the idea of finding speed. So if I put X is 2 into here, I'll get distance. But then if I say, okay, well, what happens if I put X equals 2 into this function? Well, when I put X equals 2 into this function, so I do it again with my red though this time, doing with the rate of change, that's going to tell me how fast was I going at that point. And by the looks of it, especially because it's going downwards, that means I'm going minus 3 kilometers per minute. So when I get that number, when I put that X equals 2 in there, I get that I'm going minus 3 kilometers per minute. That's the rate of change. That's how fast that is right there. Okay. Well, let's see if I can do it. 1. So let's see what happens if X is 1. So I put X is 1. Let's see what we get. 1 minus, oops, right here, derivative here. So what happens when I put 1 in? So when X is 1, 3, let's do it down here so you can actually see. I won't do it in my head. So let's do an extra one. Let's say I want to know what happens, what's the speed? What's the velocity? That's another word for it, at X is 1. So when X is 1, what's my speed? Okay, it looks like when X is 1, I'm going to be hitting that peak right there. Let's see. So what's the speed at that peak? 3 minus 12 plus 9, that is 0 kilometers per minute. So what does that mean? It means the car has effectively stopped moving. There is no speed. It's not increasing or decreasing in speed. Okay, it stopped moving at that moment. And actually that makes sense. Look at your line. It's a horizontal line. And what kind of slope does a horizontal line has? It has a slope of 0, meaning it's not increasing or decreasing in speed. It's not moving at all. There's no change in speed at X equals 1. Okay, but is there a distance? Yes. At X equals 1, I have moved a distance of 4 kilometers, but the speed is 0. And that happened from the derivative. So the function itself is showing distance, but when you say, hey, I want speed, and you want kilometers per minute, because that's a rate of change, speed is a rate of change, how did something move? That requires a derivative. Let's talk about what's down here. So let's say someone has a function that already represents a rate of change, maybe like speed. So again, let's talk about this a little bit in reverse. So now I'm working from the opposite way. Okay? Now I have the function for speed, right? So my graph, I have a function already representing speed. It depends what you can measure, right? In some applications, it's easy to get rates of change, so we can actually measure how fast something is moving easier than how much it's moving. And sometimes it's easier to measure distance and figure out speed after. So it kind of just depends in real life on what's easier to measure. Some quantities are easier to find than others. We deal with what we get when we get it, essentially, right? And math will make everything work out in the end. So if we start off with a function in speed, kilometers per minute, this is the function that represents kilometers per minute. So X is my minutes, Y or F at X is my kilometers per minute. Okay? So if someone comes to me and says, I would like to know how far you have traveled in 2 minutes. Okay, how far have you gone in 2 minutes? What they're asking me to figure out is the total distance I have managed to travel in that time. This line represents speed now, not how far I've gone. But when someone says, oh, how far did you travel? What they're looking for is kilometers. Well, I don't have kilometers. I have kilometers per minute and minutes. And how would someone get kilometers from kilometers per minute and minutes? Well, they could multiply them. Remember how units cancel? Kilometers per minute, when multiplied with minutes, will result in distance. So which application will take the y unit and multiply by the x unit to create kilometers? So I have something that represents speed. I have something that represents time, but I don't have something that represents distance. So if you come to me asking for distance, I right now don't have a letter, y or x, that represents that thing, kilometers. I don't have anything to represent distance. But I do have these two. So is there a way I could get from one to the other? Well, I know how units work. I know that if kilometers per minute were to multiply with minutes, that would make them kilometers. Now I couldn't say, well, what about using a derivative? Why not just use a derivative? The problem with saying that you're going to do a derivative is y over x. So if your y is in kilometers per minute and you say, I'm going to take the derivative again, you're going to end up with y over x. And that equals kilometers per minute squared, which, interesting enough, is the way to get acceleration. But not distance. So that's how we actually get acceleration, is by doing derivative again on speed. But the units wouldn't work out here. So for a derivative, we want to have units be y over x. But when you integrate, when you use an integral, you're going to have units y times x. And that's what I want in this case. If someone comes to me asking for kilometers, I can take my y units, multiply by my x units, and be left with what I want. So since someone has the rate of change formula and they want me to essentially remove this, the way I can remove that unit is through multiplication, which is essentially through this idea of integration, is removing that and going back to the original distance function. So if I integrate, then I will have my distance. Okay. So I hope that helped a little bit, maybe give you an idea of what we're going to be doing in our applications. And all right, let's try an application and pay close attention to what the functions are representing, as well as the units that we are in, as well as the units we are after. So the average weight of a boy whose age is between 0 and 36 months, or 0 and 3 years, can be approximated by the function WT 8.5, 1.8t minus 0.06t squared plus 0.0008t cubed, where t is in months and W is weight in pounds. So I've got a graph over here to help us represent the concepts, but here is the weight in pounds, and here is time measured in months. Okay. So one of the things we are looking for in this case is rate of change of weight with respect to time. So what I'm looking for here is the rate of change with respect to the weight, and what I have is a function representing weight. So rate of change of weight would mean pounds per month in this case, since I'm doing it with respect to time, and this is in months. So a rate of change would be another word for us for slope, which is another word for saying changing y and changing x. And what y represents is pounds, and what x represents is months. So we are looking for actually pounds per month here. So we know that since we have a function representing weight, WT 8.5, 1.8t minus 0.06t squared plus 0.0008t cubed. So this is currently the function that represents weight, but not rate of change. And we've learned through studying derivatives that when you take a derivative, one of the words we call that is the rate of change. So since I know how to take the derivative, if I take the derivative of this function here, using what I know, this is 0, this is 1.8, this is going to be 2 times 0.06, which is going to be 0.12, and this right here is going to be 0.00024. I might add an extra 0 there when I said it out loud. 0.0024 t cubed. So this is now a function for rate of change. This represents pounds per month. This represents just pounds. Okay, that's what we get when we change and we take the derivative. So when it asks for find the rate of change with respect to rate of change of weight with respect to time, that's what we have done by finding the derivative. Now just below, we have a question asking for the weight of the baby at 10 months of age. Now, this is asking for weight, which means I need to go to the appropriate function in order to get weight. This represents weight, this is rate of change. So since it wants weight at 10 months, I go to the weight function and I sub in my value. There we are there. Times, here we go, 21.3 pounds. So at 10 months, we have 21.3 pounds. Let's see here. Here's 10 right here. We should be along the y-axis at about 21.3 pounds, which looks pretty close. Okay, so my lines aren't straight, but yeah, that looks like that's what we're getting. So you can see if this is the function that's plotted, this is the WT, the weight function, then when I actually just look for a point on it, I'm getting weight. The very last question being asked of us is the rate of change with respect to time at 10 months. So here they're looking for how fast the baby is growing, essentially. So at 10 months, if I go back now to the function that represents how fast the baby is growing by month, and I sub in 10, we can see how fast the baby is growing. So 1.8 minus 0.12 times 10 plus 0.002, and we have 0.84 pounds per month. So we've got a baby growing, increasing. So weight increasing since positive. So the rate of change is positive, so the weight is increasing. And you can kind of see that back here when we look over here. If we look at 10 months, if we were to try to draw a tangent line where it's just cutting through that line in that one spot, just like this, you can see the slope there. We've got an increasing slope, okay, matching our one below. So this here represents the slope of this, the rate of change, whereas part B is just looking for the weight, which is the y value. So you can see that depending on what you want, you can gain a great deal of information either from the function itself or from the derivative.